Morning.
Okay.
Really? Just refresh.
You ready, Arash?
Yeah.
Excellent.
I'm actually broadcasting.
What's that?
I'm actually broadcasting that live.
Cool.
For a number of friends.
For what?
For a number of friends.
That's fantastic.
Also my parents.
Awesome. Which software are you using to do this?
Google Hangout.
Okay. Not anything too fancy. That's good.
It's just-
It should work fine.
It's on YouTube. We should be live.
Nice.
You can.
So we're just waiting on Tony.
Is 2020's not
No,
coming,
he will meet with me at 1:30.
What?
He will meet like afterwards. He has something to do.
Okay.
All right, so I think since everyone, the committee's all here and we're all semi-settled, so this is, I'm really happy to introduce Arash. Everybody knows him, so I'm not really going to introduce him. But this is Arash's PhD defense, and it's fantastic. He's been fantastic to work with over the last several years. He's worked closely with me, Eric, Todd, Amanda, kind of everybody on his committee. And he's going to tell us about all the stuff that he's been doing over the last few years and how it's been going. And so just let him go ahead and get started.
Yeah,
Thanks.
Thank you very much. Thank you, everyone. Well, and thank you for joining me today for my PhD dissertation defense, entitled as A Computational Study of Momentum and Scalar Transfer in Urban Areas. I'd like to start with a quote by Albert Einstein. Albert Einstein once said, "Computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. Together, they are powerful beyond imaginations." In this study, we want to improve the understanding of urban weather, the weather around us in buildings, and basically in cities, which is known as urban microclimates. And to do so, we will use various computational methods and software applications. We will focus on the impact of urban infrastructure elements, like building geometrical parameters and the morphology, on the flow structures in complex areas. And we will focus on three different aspects. First, we will zoom into the city and look at the fundamental elements of the city, known as street canyons, look at the structures there. Then we integrate these fundamental elements at city scales and look at the morphological characteristics and how they're correlated with the flow structures at city scales. And finally, we want to go to the broader scales at broader time scales. And to do so, we're introducing a fast response HPC software for doing diurnal cycle simulations over city scales. Okay, sure. Now, before we start, you may ask, why does this matter? According to recent studies, more than 54% of total population reside in urban areas, and it is predicted that by 2050, this amount would increase up to 65%. This urbanization causes deleterious effects and harmful microclimate phenomena, such as air pollution and urban heat island. Basically, air quality, that means that the air pollution will cut, it is a risk factor, it is a leading risk factor for death and environmental disease. And the urban heat island will cause ecosystem danger and discomfort to the urban residents. Now, throughout this study, now let's see that if we want to do these sort of studies experimentally, we will have several challenges in measuring different momentum characteristics, in measuring the wind speed, in measuring pollutant concentration, and energy transport. So we do need to use various computational methods for such studies. And throughout this study, we will use computational fluid dynamics, which solve the transport equations on a gridded domain. And we use the three categories of these methods, starting with fast response models, which solve for the mass conservation equation and use several parameterizations to get the mean velocity field, to get the mean flow characteristics. Then you have the Reynolds average Navier-Stokes RANS, which is actually the most typical CFD method used so far. And this one will model the turbulent fluctuations using a turbulence closure model. And the last one is the large eddy simulation, which resolves the large eddies instantaneously in the field and uses subgrid scale models to account for the smaller scales and smaller eddies. Now, if we sum up all these three methods in the figure shown here, if you assume that the signal, the black, is the original signal, RANS and QuickERB may predict the feature as a straight line, which is the mean fluctuation, which is the mean, the average of the entire signal. And Elias would try to follow to actually simulate the major fluctuations in this signal. Now, looking in more details, this is like QuickERB. It's a component of QuickERB industrial complex dispersion modeling system. And it is a 3D wind solver, which uses several parameterizations for flow algorithms in cities. In like any urban area, it uses algorithms for wake zones, for rooftop recirculation, for in-canyon cavity. It solves for the mass conservation, but doesn't satisfy the momentum conservation, and instead it solves for a Poisson equation with the constraints of being mass conserved and the initialization based on the several flow algorithms that we import to this code. And as I said, it is semi-empirical. So here you see some of these zones that we define based on the experimental data that are available for different zones of the city. The second model is RANS. So this model here is a Boussinesq airflow system, and it has a turbulence. It has a K epsilon RNG turbulence closure model, and it uses semi-implicit pressure solver, and it solves for the TK production and TK dissipation, as you see here. And we are collaborating with Dr. Kim from Kokyung National University of Korea to get some of these results with his RANS model. And the third one is the Elias model. It is in the platform of Uinta MPMIs. So Uinta MPMIs is a massively parallelized, fully coupled modeling system, and it is actually a fluid structure interaction code. And Uinta basically has two major components, the ICE and the MPM. So MPM stands for Material Poise Method, In this method, you create any object using a cloud of particles that come together, and it solves for the structural mechanics in a Lagrangian grid. As you see here, the particles have an initial state, then the states are interpolated to a grid that you have in the domain, and then the status of this mesh is updated, and so does the velocity in position. And finally, you get to reset this mesh and go to the next round. Now, from the fluid solver, which is called ICE, implicit compressible Eulerian, which is actually an Eulerian fluid solver, and it is a finite volume, fully coupled, and it's multi-material fluid solver, which solves for the conservation of mass, momentum, and energy. And you see here that the coupling between the ICE and NPM occurs through this momentum energy exchange forces. And we also use a dynamic Smagorinsky model to resolve the smaller eddies in the domain. Now, let's talk about the first topic. Now, you're in the city. Let's zoom in to the fundamental elements and look at what's going on inside a street canyon. You may ask, what is a street canyon? So basically, it's a street that is surrounded by a group of buildings on both sides, as you see. And on the right-hand side, you're seeing like the wind is coming from left to right, and as the wind blows, it gets trapped inside this this canyon, and you see these recirculation patterns occurring between the two buildings. Now, the question we want to answer is, what will happen if we change the morphology of this canyon? If we have different types of buildings, if we have taller buildings, shorter buildings, what will happen in that case? And looking at this flow structures, one case might be a step-down street canyon, where you have a high-rise building followed by a low-rise one. And here we will look at the impact of this canyon width, shown with S here, and the downlit building height shown as HD. And we want to see how does these parameters change the flow structures in step-down street canyons. And here are the results. You will see a wake-dominated flow regime, which basically means that the canyon cavity inside this this street canyon is strongly influenced by the wake of this upwind building, if you look at the side view. And as a result of the equilibrium from the vertical motions and the horizontal motions that you see on the top view, you will have an in-canyon flow separation. And you see this as like with this white circle there. And you also see this flow equilibrium zone. And we also have from the top view, we know that there is a flow separation occurring from the leading edge of the upwind building. And here again, you see that the sidewall flows are coming into the inside the canyon, and through the interaction with the wake of the upwind building, you will have this this flow structure here, which will appear as a flow separation on the side view. Now, we want to quantify these flow structures using some representatives. To do that, we use topological features. So basically, these are the critical points that could probably be sources of high concentration and high energy, like high temperature, based on the topological features that we might get in a city. So here, for the case of step-down canyons, you will see a primary vortex, a saddle point at the middle, at the top right of the canyon, and the in-canyon separation point that we showed in the previous slide, plus the possibility of secondary vortices at the edge of the each of the buildings. Now let's look at how these three different computational methods work in this case. So here we'll look at the performance of Quick-Brand's Elias versus the experimental data coming from wind tunnel measurements of a former PhD student. So here you see that in general, all the three methods capture the general wake-dominated flow regime, especially like on the primary features. They all capture this vortex core, as you see with this black check mark. But on secondary features, that doesn't happen all the time. And only, for example, LES can get this in-canyon separation point. Now, let's see what happens if you change the height of this building, which is the downwind building. Here we show this example, and here we want to see how well can we follow the dynamics, can we track the dynamics of these major topological features in the canyon. Here we are changing the height of the downwind building, and looking at these results, you will see some interesting features. For example, in vortex core, you see that while most of the methods predict that it is this vortex core is moving to the right side of the canyon, let's say from left to right, in some methodologies, it got stuck. It's like a static feature there. Also, in canyon separation, you will see that only LES can capture the correct dynamics, which means that the in-canyon separation is moving to the right as you are increasing the height of this building. Now, looking at another test case, just another sample would be a step-up canyons, where you have a low-rise building followed by a high-rise one. You see totally different flow characteristics, flow regimes. So here we call it like the non-classical flow regime, in which part of the flow skips over the rooftop of the upland building, and part of it gets trapped inside. And you might have the possibility of rooftop recirculation, as shown here. And from the top view, you see that, for example, for this case of wide buildings, you see this shielding effects, which means that most of the flows are getting out of the canyon and doesn't come inside from the top view. You also see these gigantic vortex cores, which are in the wake of this downwind building, and it goes up to more than 4 width of the building. Then to sum up these topological features, in this case, is if we categorize them the same way we did for step down canyons, you will see the possibility of rooftop recirculation on both buildings. You also see stagnation points and primary vortex in the middle of the canyon, plus the possibility of secondary vortices. Now we have studied more than 25 different test cases and tried to classify all our information based on the flow regimes in the canyon. And here is what we have found for, based on all of our studies, we have identified the non-classical skimming flow regimes, the wake-dominated flow regimes, the deep canyon skimming, and the classical skimming, which is the typical one that happens all the time. And now we want to provide a guideline for the usage of these computational methods and see how we can use the hybrid. We can probably use these combined methodologies to capture all these features. In order to do that, we're defining target-dependent metrics as follows. We have the fidelity, which basically is the accuracy of a computational method in capturing this topological feature. We have the computational cost, which we relate that to the required time of the simulation. And we have the efficiency, which is basically the ratio of the fidelity to the computational cost. As a result, we will define a metric called applicability, which we define that as the overall performance of each computational method in predicting specified topological features. And you see the definition is here. It's basically, it has more important, the more importance is on the fidelity, but we also consider the computational cost to get the applicability of each method. And here is the guideline that we provided for this. So basically this guideline will give you a like regime versus feature, and you see that how different methods can be used for capturing these dynamics. For example, as you see, like RANS has the highest applicability in street canyon flows, and you see that, for example, for stagnation point, for saddle point, and rooftop recirculation, they have the highest applicability based on our metrics. For some features like separation point, only the LES method can capture that. And we are also working on quick ERB to make it better. And you can see that for now, for example, for primary vortex with deep canyon ischemic flow regimes and classical ischemic flow regime, quick ERB is actually doing good. Now, moving on to the next chapter, let's now zoom out a little bit and see what happens if you look at the integration of these canyons at a city scale. Here, we are replicating the downtown of Oklahoma City. Basically, this is a field experiment from 2003 in the downtown of Oklahoma City, in which valuable measurements for momentum and scalar field were available for evaluation studies, and that's why we focus on this test case. And here is the region of interest shown with this red box there. And we have almost constant wind direction during the time period, the 30-minute time period that we are working on. And we have the release of the plume at the center. It's not the center, it's like this location, which we have the sulfur hexafluoride release for 30 minutes. And then look at the concentration of scalars in this field. A little bit on the computational setup for this simulation. We're modeling actually about 67,000 geometries in a domain of 2.8 kilometer by 1.3 kilometer at a very high resolution of 1.5 meter. And we are using more than 2 million CPU hours on 16,000 cores. And for modeling, for accurate modeling of the surroundings and the inlet, we're using a concept of numerical grid turbulence generation and the surface roughness elements, which I refer you to the paper from 2017, which we extensively discussed this. Now you're about to see the visualization of this scalar that was released at the middle of the canyon. And here you will see 20 terabytes of data in 20 seconds. So 1 terabyte per second is what you will see here. So basically, here you will see that the plume starts with in the middle of the canyon, and as it gets to the north, here, the width of the plume increases. You see some instantaneous features, like sometimes the width of the plume gets much higher up to this point, but other times it's not. So there are a lot of unsteady flow motions that are happening with this like plume distribution in this city. So now let's look in more details at what's going on in this city. So here is the mean pollutant concentration. We call it the scalar concentration. And we divide the results, the findings, to 3 zones: the northwest, the northeast, and the near source. Looking at the northwest side, you will see that with our methodology, we are capturing the plume channeling effects up to the northwest side of the canyon. So here are like the farthest locations from the plume source that we're capturing this plume channeling effect. Sometimes we are underestimating the concentrations. On the northeast side, surprisingly, you're capturing the correct plume shape. Basically, this circles are the experimental data. It shows that the plume doesn't reach this point, and we are capturing this correct feature. Surprisingly, again, we have weak channeling effects on the very first channel. And now, to look at the statistical analysis of this, our findings show that the results for mean scalar transport, for mean scalar concentration with our methodology is significantly better than the previous literature studies on this, while at the same time for mean wind characteristics, we didn't see that much of improvement. This came up to this idea that the mean scalar transport is more dependent on correct modeling of the unsteady and instantaneous features, which are strongly correlated with correct modeling of the turbulence characteristics. Now, to go deeper on the turbulent characteristics, we can define an arbitrary signal. Here is like the velocity. You can define that in a time-space scale, where you have a signal as a combination of a time average, a time-space average value, a turbulent fluctuation, and also the fluctuation of the time average with respect to the space average. So basically, we are dealing with space as another averaging domain, as another averaging scale for our study, in order to get like a representation of the entire like city in 3D. Here, like using this methodology, you can get the combination of, you can get the TKE transport. TKE equation is just like the combination of shear production, weight production, dispersive transport, and the other parameters you see here. We didn't look at the triple correlations, so that's an oops, but because we don't have like some of these terms for our calculations. Anyway, like this is the shear production, weight production, and dispersive fluxes. So what these parameters show is how the turbulent fluctuations are generated, are removed, and are transferred to different layers in our 3D, in the city, at the city scale. Here we classify this time-space fluctuation characteristics. We classify them based on the layer that we are in the city. This figure on the top, this one shows the vertical distribution of the streamwise momentum flux. So we define a UCL layer, which is basically called the urban canopy layer. It starts from 0, goes up to the mean building height. Then you have the roughness sublayer, which starts from the upper UCL and goes up to 5 times the height of the average height of the building. And above that is debatable, but it's called the inertial sublayer. So some interesting features we have found here is that there is a possibility of positive momentum flux, which means that we are adding momentum at the near ground surface. And the other thing is, looking at these shear production, we have found a dual peak in the vertical distribution of our shear production, which is correlated with the morphological distribution of the city at 2 different scales. First one is the UCL height, which is basically the entire average of the domain. And the second one is the second group of buildings that have like let's call it a second average, when you have a number of buildings at a certain building height. And you see the second peak occurring at this limit. The other interesting thing is that the shear production doesn't go suddenly to 0 at the top of this UCL, and it continues up to high above the canyon and close to the tallest buildings. Now, if we want to look at how the distribution of these buildings, how does that change the turbulent characteristics, we need to look at multiple zones. So one way to do this that we came up with was to split this domain into multiple subdomains, and then look at these turbulent characteristics at each subdomain and see, do we find correlations to the flow characteristics based on what we see in different subzones. Interestingly, we have found that there are linear morphological correlations between the vertically averaged turbulent characteristics and the urban canopy layer height. So we have looked at the maximum building height, we have looked at the plan area fraction, which shows basically the arrangement of the buildings in that subdomain. And we didn't find strong correlations in that. But surprisingly, we see that what dominates the mean production of turbulent fluxes, dispersive fluxes, and weight production and shear production is dependent mostly on the average building height at each subzone. Now moving on to the final task. So here, up to this point, we look at fundamental elements, and we move them at city scale. And we looked at over 30-minute time period. So for more realistic situations, you're looking at modeling these urban microclimate characteristics at a much larger time scale, let's say up to cities. And in order to do that, we need to have a fully coupled environmental simulation software that can handle different processes that might occur inside an urban area. So you can see that, for example, you have solar radiation coming to the city. You have reflective radiation, like reflected back with albedo. You have conductive heat flux to the ground. You have conduction through the walls of the buildings, and evapotranspiration. So all these fluxes need to be modeled in order to do a dynamic modeling of urban microclimate at a large time scale, let's say up to days of simulation. In order to do this, we are introducing a fast response, high performance computing software entitled Quick NVSIM, which has 5 different solvers in it. You have Quick Earth, which I already talked about, and Quick Plume, which these 2 solvers will calculate the mean turbulent wind solver, the mean turbulent wind characteristics. And then we have the QES transport, which solves the distribution of an arbitrary scalar throughout the city. And we call it the scalar transport solver. And finally, we have QES LSM, which is the surface energy balance model solver, and the radiative energy solver, which is called QES radiant. So these are like completely coupled, and I have slides to talk about like the exact coupled mechanism, which I can talk about if I get time. On the QES platform, what we are using is we are using a hybrid CPU-GPU platform in which we use NVIDIA's CUDA programming language, NVIDIA's optics for ray tracing, and we use OpenMP application programming interface. Some of the interesting features of QES for now is the 300% faster than real-time capability of this code. So this basically means that you can model a 24-hour diurnal cycle in the city in less than 5 minutes. And the average execution time per time step is pretty low, is about 0.03 seconds. And we also have the capability of coupling this software to other building energy type solvers like Energy Plus. And QES runs on single GPUs. Part of it runs on GPU clusters and has the potential to be executed on a cluster of GPUs. And the thing that results in these speed of the code is the low latency, low communication overhead. And as a result, we are getting a linear scaling up to more than 3 million data points, as you see here. And QES is now fully, it is now accessible through data files with data visualization softwares like Visit, which we use, as you see in that movie, and also for data analysis with Python, MATLAB. So basically, we provide all the data set that are needed for analysis of these microclimate studies. So talking a little bit about the details of QES solvers. QES Radiant, as I said, is a ray tracing radiative heat transfer solver. It basically solves the balance of incoming and outgoing shortwave and longwave radiation based on the reflected and incident radiation coming going out of the city and coming to the city. And it starts with resolving the surface using surface discretization. So basically, we discretize any surface into a number of patches. And then will launch the rays from the sun, if you call it, and then you have a disk that these incident rays coming to the disk, and then you have a scattered radiation, which is a sphere around any patch that you see the reflection of this radiative fluxes, and you also have the diffuse long-wave rays from the surroundings. More details of this can be found in Overby 2016 Urban Climates paper. And we also have the decoupled momentum scalar transfer calculation. So here is interesting. We are solving for the transport equation, but we are using a trick. We are not solving for the velocity inside this scalar transport. So basically, we take advantage of the results from QuickURB we defined early on, and we also use for modeling the turbulent scalar flux, you're using a K-theory. And to do this, we are using the this stress tensor from the quick plume solver, which basically solves for the TKE field in the city. And this is, you can find more details on the implementation of the scalar transport in a master's thesis by a previous student, Briggs, in 2014, and more about the quick plume in Williams 2004. Now, in QES LSM, we are solving for the energy balance on each surface. So we do have the net radiation, we have sensible heat flux, ground heat flux, conductive heat flux, and the evaporative heat flux, which call it the latent heat flux. We are modeling the sensible heat flux using two different equations. One is for high winds, and the other one is for low winds based on a constant convective coefficient. And the high wind one is based on the standard K epsilon Ball function. And for ground heat flux, we are using a paper that gives you the covariance of ground heat fluxes based on with the net radiation. So we are using the net radiation, and we get the fraction of net radiation based on the formulation you see here. And basically, this one will give you the lag between the maximum ground heat flux that occurs during the day with the maximum net radiation through the day. And for conductive heat flux, for now, we're using a single layer of differential finite difference method. So basically, we are doing a difference between the external and internal wall temperature. And for latent heat flux, we are using the Penman-Montet equation based on the available energy as a subtraction of the net radiation, sensible, and ground heat flux. Now, moving on to the results, here's a test case that we are actively working on. This is the University of Utah campus. We have deployed a number of sensors all over the campus. You might have seen them with like those yellowish stations that are installed on the campus. And these are like great sources to look at these diurnal cycle events. Here we look at a 1 day of the diurnal cycle on March 19th, and we focus on these sensors that are located here in like Q, K, in between two street canyons, and the WBB is the one that we use for getting the input for our simulations. And these LEMS sensors is like, you can find more about them in Gunawardena 2017, the Measurement Science and Technology. So now looking at these results, what you will see here is we are looking at the noon, and you're seeing the cooling and heating events at around noon. On one side, you will see the shading effects, which have lower temperature based on the which occurs because of the shades over the building. And you also have on the wake field, you also have the heating events. And inside this canyon, you see that the shade of these two buildings cause this cooler temperature compared to the surroundings. On the near surface temperature, this is around like 2 meters above the canyon, you don't see that much of a difference as you see in the ground temperature. one thing that you can see is like a slight heating zone in the wake field, and you see a little cooling effect on the shading zones that you already saw in the ground temperature. And you see that at some points we are underestimating this temperatures. This location particularly is in the south of MED, the Material Engineering Building. And we believe that the surface misrepresentation is causing these sort of issues because one of our findings is that QES LSM is strongly sensitive to any changes in the heat fluxes that we are calculating. So if you are misrepresenting any surface inside this campus, you might get underestimation, particularly in ground and then in the near surface temperature. In summary, if you look at these, if you look at this diurnal cycle, you will see that like the sensor E that I just talked about at noon, it has this strong underestimation of the temperature. While in some sensors like sensor K, which is between the two canyons, you see that the results matches pretty well. And this basically means that the representation of the surface characteristics is really important. And in general, we see less variations in, less error in the near surface air temperature. And this is associated with the lower variability of air temperature with respect to the inflow. So basically, our findings show that as long as your inflow for air temperature is good, you can call it good for probably most of your city. But in case of surface temperature, you see much more variations. And out of our calculations, we got an R squared of 0.56 for surface temperature and a mean relative error of 15% for the air temperature. Now, to just sum up, we first look at the structures in street level. We study the step up street canyons, step down street canyons, and finally look at even height buildings. Then we look at the integrated flow characteristics at city scales. We studied some of these correlations, morphological correlations with the turbulent characteristics. And finally, we'll look at the diurnal cycle of energy transport at city scale, introducing a high-performance computing software which can calculate up to these large timescales. Some of our conclusions are that we provided new information on major topological features occurring in the street canyon flows and how they are correlated with morphological parameters. We provided guidelines on the combined usage of these diverse computational methods for different flow regimes and topological features. We also look at the correlations of turbulent flow characteristics at city scales and how they are correlated with the urban canopy layer height. And finally, we introduced a fully coupled HPC software for integrated study of urban microclimate at large time-space scales. And we also found the importance of surface characteristics and heat fluxes on the modeling of surface temperature, and we found a strong sensitivity to these parameters. Future works, we can talk about different topics here. One of them would be, we didn't look at some more complex canyon cases where you have vegetative covers around these canyons, or when you have the shape of the rooftop actually, that we just use the flat plate for now, that might have, that does have impact on some of these topological features that we see. And also the rotation of these buildings will also provide us with some more knowledge and insight to these flow regimes in street canyons. And for improving the computational models for urban design, we are suggesting to work on quick urb canyon cavity for uneven building heights. Since quick urb is mostly dependent on flow parameterizations, if you feed it with more models, with more complex models based on more test cases, you might come up with more accurate answers. On the other hand, we're urging the improving of turbulence models, because one of the things that we saw here is the exaggeration of the vortices, the primary vortices in the domain. And we believe that by improving the turbulence models, we might get to the better answers with RANS models. And with LES, it's always debatable on how you can improve the surface boundary conditions to have a more accurate representation of the near ground characteristics. We also want to extend our multi-zone city analysis up to the scale that we see these thresholds on the correlations still occur. So this will help us to understand that based on the classification of a city that you have, how can you get a smallest subdomain that can represent the characteristics of this big city that you have. So this would be the multi-zone study. And there are a lot of improvements for QES. Recently, we have seen that the sensible heat flux is quite sensitive at nighttime. And we need improvement for near surface velocity model at low wind speeds, and also the turbulent kinetic energy at low wind speeds. And we are thinking about integrating the two components, quick earth and quick bloom, dynamically into the QES system so that we can have a fully coupled 5-solver system. Currently, it's like 3 solver fully coupled, and 2 others are coupled through the I/O input-output. We also want to add surface energy balance for vegetative elements. And finally, if we get the QES to production level, it can be served as the toolbox to study different urban planning strategies. And it can help in the future of sustainable city design. So here are the research deliveries. We have one paper published in boundary-layer meteorology. The second draft is completed and it's almost ready for submission to building and environment. We're also working on other manuscript essays. So far, we had 4 different conference presentations on like abstract poster presentation, and we have 4 different accepted or given oral presentations. And finally, I want to acknowledge my advisor, Dr. Rob Stahl. I think I learned a lot from him through these years of study and like doing effective research and the important things, and like when you look at the problems. I would also like to thank my co-advisor, Dr. Pardiak, who was always a great help for whenever we had issues in our analysis. It was like someone who would help us no matter what. So I would also want to acknowledge Dr. Todd Harmon. He helped me and taught me a lot on high performance computing from day one up to like, I think like more than halfway through my dissertation, through my research. And also would like to thank Dr. Smith for her advice on external coupling of QES to other solvers, like building energy models in Energy Plus. And finally, would like to thank my wife, Maida, for all her supports in hard times, and my parents who are not here. And I hope will watch this. And anyway, thank you very much for your attention.
So now we'll take questions from the general audience. Kick you guys out. Have questions for Arash on his presentation, or if any committee members have general questions they'd like to ask me. So, yeah.
I have a question about the multi-zone analysis.
Yeah.
Is the idea there to get what is the smallest slice of the city that you can simulate to still be representative of the entire cityscape?
Yeah, exactly.
Sure, you're seeing it in small.
Right, right. Yeah, that would be like specifically because these type of simulations are very expensive. It's like this one was about 2 million hours, and it took forever to do this. So the smaller the time the space zone would be better for our analysis. But we expect that there should be a threshold where you see, let's say, you will see some differences from the fundamental street canyon scale up to the city scale. We want to find that threshold so that we say, okay, up to this scale, these correlations occur, and we can call this good as a representative of like a larger kilometer or like couple of kilometer domains. Does that answer?
So is it that the representative slice should have the representative distribution of building heights or about spacing?
It's right. So the representative would be that. So as you see here, for example, you see that this urban canopy layer, right? Each subzone has its own building average height, right? So this building average height is correlated with the vertically average turbulent flow characteristics. So if you split this subdomain again, you will get a different distribution of buildings and a different building average height. Now we want to see, does that still correlate with these, with the current correlation that we found here, and how far can we go on this trend? If we find a good representative of the turbulent flux, the shear production, wave production, dispersive fluxes, these are the representative of the generation of turbulence inside the city. And if we find these correlations, we can say that, okay, from the turbulence standpoint, they represent the larger domain that we are looking at.
For condition distribution for the near surface, you observe that uniform distribution. And then what I do observe that uniform distribution
So here we only look at like 2 meter. So this plot is actually 2 meter above the ground. The reason for that was that we only had the experimental data up to this point. Because like these LEMS measurements are the fixed height of 2 meters. We would love to look at like higher above the canyon to see how does that change. But overall, what I can say is that our findings show that if you find the inlet temperature that we use is this WBB voltage here. So this one is about like 30 meters above the ground. So we still found that this temperature might be a good representative of the distribution at 2 meters. So we don't see that much of a difference based on what we set for the inflow condition for the air characteristics. That's exactly the opposite for the surface temperature. So we expect to see less and less variations as we move on to move higher above the Right. Yeah, definitely. Like even at 2 meter, we see smaller effects, but definitely like if you're way above the average building height, it might disappear. We didn't see that for wind transport from Elias. As you see, like here, this was actually interesting. So here you see, for example, this is like turbulent characteristics. This is your mean UCL. And we see that the shear continues because you have some higher tall buildings that are not necessarily the average building height, but even the few of them will cause this much variation in the characteristics even above the canyon. And this would be up to the RSL.
What question that doesn't account for
Yeah, exactly, it doesn't. Let's go. Oh, yeah, so you see these regions that we defined, like let's say between two buildings. These are like empirical formulations and formulated models to represent the structures that we observe in the canyons. These are mostly based on empirical parameterization, based on experimental data, like wind tunnel data sets. So if you have sufficient data, you can feed that to this model and make like complex models that can represent these structures in the canyons. And this is like the trick that we want to use to avoid solving the full momentum equation. Because if you do that, there's a high possibility that you cannot get it to a fast response model, to that level that we want. So this is a cool idea to have it conserved. And since you have a lot of buildings together, it might actually work. And we have seen that it works for, let's say, even height buildings, classical models, classical scaling flow regimes. Now we want to improve this based on these parameterizations.
Do you go into details about the radiant boundary conditions you're using? QES rad, in particular the sun and clouds and building.
Right. So we are modeling, for now, we are not considering the cloudy days. So we just assume that there is no cloud coming yet. For the surface condition, we are using the temperature. We initialize the patch temperature based on some initial values that we have for the patch temperatures. And for the fully coupled one, we are using LSM to feed this system. So this would be like the dynamic. This would be the dynamic coupling of transport, LSM, and radiant. So detail inside the radiant calculation, I would refer you to Overby, who wrote this like the entire ray tracing radiated heat transfer solver. But from my standpoint, we're using the coupling of ray tracing calculations, the sensible heat flux, and other terms, and we come up with a new surface condition at each time step and feed this surface condition to the transport equation. And this would be like the way we do the dynamic coupling of the system.
What about the sun? Is that taken into account?
Yeah, it's just you have the sun as a disk above the entire city, and you do like a spherical ray that's coming to the entire building, based on each patch.
Great talk. First of all, a couple of questions, but since you're recording this, I'm going to just ask some of them.
Sure.
So, first thing in your slide 42 about the ground temperature, there is a much higher temperature in the wake zone, basically, of the building. Can you explain for me why that is happening?
There are two possibilities for this. One is that it comes from the high surface temperature around this wake zone, like the surface temperature, the ground temperature right at the building site. That can be one possibility. The other thing is that this will come because of the low turbulence mixing at the wake zone, which might be a defect of the cut. Which means that if your fluctuations are not high enough here, you will find like this heated zone that is not mixing with the surroundings enough, so that we see this like a heat zone. We have seen the effects in the TKE model, that we use in the quick plume. That is one of our hypotheses. So we're not still completely sure about that, but we have seen like some of these trends.
So that those less fluctuations can basically. I want to link to the other question that I asked in Carlos defense.
Yeah.
About the convective heat transfer.
Yeah, here you see that.
So can that be a reason that like we can have a lower basic convective heat transfer, or that's just fluctuations? What I'm trying to ask is that so the fluctuations that you said, does that affect only the convective transfer coefficient, or it's changing the flow?
Okay, so that will impact the whole system in the sense that if you look at like 2 points, if you look at the transport solver, so here we talk about that trick using quick error and quick plume for the stress tensor. So here is when you will see some of that impact inside this scalar transport calculation. This one comes completely directly from the TK calculation in quick plume. That is one location for that. The other one would be in the sensible heat flux here. We know that the quick ERP model doesn't work well at velocities below 2 meters per second. And for higher than that, if you're using completely like this one is the TKE actually. And you see the direct impact of that on the sensible heat flux here. And in a global sense, now that you have the balance of this, and since this is what runs the entire system on the new boundary conditions, the dynamic boundary condition can affect the whole system, as it provides you with the new temperature conditions for moving to the next step.
Another question about the graph that you have for solving one is some
Oh, the QES? Okay.
this one is just the execution time for only the QS transport, gradient, and the LSM, or is included for the time execution time of quick error and as well?
Yeah, so this doesn't include Q, like quick error and Q. They are only coupled through the I/O. I will probably, it's a good idea to show you this diagram here. Here is the entire system. So these two, so you start with like reading geometry from quick error, then read the turbulence characteristics from quick plume. Then you set the surface properties, date and time, and here is the entire loop that is going through. So these two parts are standalone. And the idea, one of the future works would be to include these two solvers inside the QES. Because we want, probably they want you to do. We want to have this dynamic system for everything. So that instead of doing this through I/O, we just have that internally coupled with all these solvers.
The reason that I asked it was that if we already the quick error, quick plume, and the QS is working that fast, why we need to that was
Oh, yeah, yeah, but it's not.
And everything that he did run is on.
It's still a little slow.
You have a lot to work on.
Thanks. Are there other questions from the general audience? All right, well, let's thank Arash again. Head outside. Except for the committee, because the committee can head outside if they need a break. As long as you promise to come back.